Hi everybody. Today's lesson went up very late today, but that's okay because it's the weekend and this is the last lesson of this entire unit. So you have to do this work and then we're going to do some review work and another quiz and a final test in this unit if that's the way we're doing it. I'm not quite sure yet, but today's the last day of work and you have all weekend to get to this work whenever you want to. The last lesson is called Universal Gravitation. And this is force of gravity, but this is force of gravity in a much more general sense. Because here's one of the problems with what we do with force of gravity. Let me put a page down here in front of this one for a moment. You were calculating this when we were doing force of gravity. You were calculating that force of gravity was, you take whatever the mass is and you multiply by g. And in our case here on Earth, g is 9.8 meters per second squared. Well, Newton had a problem with this because, number one, you're not accelerating. If you're sitting in a chair and you're going to calculate your force of gravity, you're not falling downwards at 9.8 meters per second squared. I guess it probably does make a little more sense if you say 9.8 newtons per kilogram, because then at least it stresses that there's 9.8 newtons of force on your body for every kilogram of mass that you have. But still, you're not falling. You're certainly not falling at 9.8. And the other thing is this value of 9.8. You have to know that value. What if we want to do a force of gravity calculation on the moon or on Mars or on an asteroid? We don't want to have to go there and be on the surface to try and discover what the acceleration due to gravity is on that surface. We need to know it before we get there. So Newton wanted to create a much more general way of calculating force of gravity, and that's what universal gravitation is. So the word universal doesn't mean space, and it certainly doesn't mean the universe. It just means that this frees you up from the restrictions of having to know what the acceleration due to gravity is when you're trying to calculate force of gravity. So Newton wanted a situation like this. Newton said that whenever you have a mass, and there's another mass in its vicinity, those two masses attract one another with a force. And that's the force that he called gravity, the warping of space by one mass and the warping of space by the other, causing them to fall together or attract together. So you could apply this same diagram to you right now. Mass number 2 could be the entire Earth, and mass number 1 could be you. It's just the distance between the two objects is you're touching it, you're on the surface of it. But let's go a little bit more general and talk about objects that are completely separate from one another, not like things sitting on the surface of the Earth. And if you read this question here, example number 1, it really stresses it. Two spherical objects, one has a mass of 4,000, the other has a mass of 6,000, and they're 1.5 kilometers apart in space. What's the gravity between the two? That's what we're going to be calculating. And in order to do that, you have to use the universal force of gravitation formula, which looks like this. It's still capital F. It's still force of gravity. You could even write a little g after it. But the formula for it looks as follows. Capital G, not lowercase g, capital G, mass number 1, mass number 2, and those are all multiplied together, divided by the distance between them squared. And it's a little bit confusing because we're using 1s and 2s on top as object numbers, and you can see they're in the lower right hand corner, but on the bottom though, the distance between the objects is actually squared. So you have to make some kind of a note to yourself that this is an exponent. That's a math operation. These are not. This 1 and 2 could be a and b, or x and y, or you could call them whatever you want. But on most formula sheets, you see them written as that. So just filling in the side here, M1 and M2, those are masses. And standard metric units, they have to be in kilograms, never grams, or any other mass unit. D is distance. And as usual, it has to be in meters. And more specifically, this distance has to be center to center, always, when you're doing the calculation. G is the universal constant. And actually, I'm going to write that in there. Universal constant. This is a value, and this is a value that was determined after endless derivation, and it's a very strange value. It's going to be awkward the first time you write it down. The universal constant value, and it's on your formula sheet, by the way, when you get to tests and quizzes and the exam. The universal constant value is 6.67, very specific, times 10. It's a scientific notation number. 6.67 times 10 to the negative 11. It's a very odd looking number. It's extremely small. Think about what that means. To the negative 11, that's 0.0000000, 10 zeros, and then finally 667. 6.67 times 10 to the negative 11. And the units are also very unusual. Newton meters squared divided by kilograms squared. So this looks like it's going to be very confusing, but actually it's not. It's a very simple formula and a very simple substitution, and it's not until you get to grade 12 that things get a little bit more complicated. So going on to example 1, if you wanted to do a simple calculation for the force of gravity between these two objects, it's literally just subbing into the formula. So the force of gravity here, this is out in space. There's no Earth in this question. There's no force of gravity with a planet. It's literally just one object and another separated by a distance. What's the gravity between them? Force will be capital G, m1, m2, divided by distance between them squared. And so that distance is going to be this. From the center of one to the center of the other, what's the distance between them? And in questions like this, that's the distance that's given. You don't have to worry about radiuses and things like that. So there are two masses in this question and a distance given. The masses are already in kilograms, but the distance isn't. It's 1.5 kilometers. So that's going to have to be adjusted. This is going to be a long substitution line. I don't know exactly how long, but it's the G value that makes it long, because you have to write that in there. 6.67 times 10 to the negative 11. And if you're following what I've been telling you all semester long, you always want to put units. That's Newton meters squared divided by kilograms squared. That's going to be followed by two masses in this question. One of the masses is 4,000 kilograms. And the other mass is 6,000 kilograms. And the distance they are apart, and you have to adjust the units here, 1,500 meters. And somehow the most common mistake that you have to remember not to do, or not to forget to do, is you have to square the bottom. Always. And I guarantee on the very next quiz, many people in the class, that will be your mistake. You'll forget to square the bottom. And then it's just a matter of taking a calculator and doing the calculation carefully, especially the scientific notation portion of it. So I really, really encourage you to not just write this answer down, but try it on a calculator and see if you can get the answer, because if you don't get this exact answer, you're punching it in wrong. It comes out to 7.115 times 10 to the negative 10 newtons. An extremely, extremely small force. So masses like these that are only 4 tons and 6 tons, being a kilometer and a half apart in space, there's barely any gravitational pull between the two. You really need planetary-sized masses. So when we get into things like the sun and the earth and even the moon, that's when you start to get forces of gravity that are very strong. Now, the only other thing you're going to have to do with this formula in grade 11 is, other than make sure you're adjusting units, you may have to rearrange the formula and solve for other things. So if we go on to example 2 on this page, that's what this question is about. So this question tells you the force of gravity that holds the moon and the earth, well, holds the moon in place going around the earth. So it says the moon has a mass of 7.34 times 10 to the 22. Earth has a mass of 5.98 times 10 to the 24. And it says in this question, if the force of gravity holding the moon in orbit around the Earth is, sorry, I blanked it out with my marker there, 2 times 10 to the power of 20 newtons, a huge, huge, massive force, solve for the distance between the Earth and the moon. So in this question, we are solving for this instead. What is the center-to-center distance between these two masses in space? So normally, the formula would be capital G times the two masses together and divide by the distance squared. If we want to rearrange this formula to solve for distance, I'll bring the d squared up to the left and bring the force down and write it like this instead. D squared will equal G m1 m2 multiplied by F. And then you can do one of two things. You can get rid of the exponent of 2 and square root the entire right-hand side, or you can just remember that you have to root your answer in the end. I prefer to do it right away so I don't forget. So I'm going to write it like this. I'm going to root the entire right-hand side now so that I don't forget to do it later. And then as long as you do the isolation right, it's just a matter of substituting in and doing your bed mass carefully. So 6.67 times 10 to the negative 11, that value is never going to change. Anytime you use capital G in a formula, and that's why you always write it as a capital. Capital G in science is recognized universally as the universal gravitation constant. 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. This is actually going to be a really long substitution line because of all the scientific notation. I didn't give myself enough room. The mass of the moon, 7.34 times 10 to the 22 kilograms. Mass of Earth, 5.98 times 10 to the 24 kilograms. And normally you divide by the distance between them and you square it, but we've rearranged the formula. So here we're just dividing by the force. And remember not to square it because it's just a capital F. The force was given in this question as 2.0 times 10 to the 20 newtons. And if you're really keen on looking and seeing how calculations work, newtons cancels with newtons in the gravitation constant units. Kilograms, there's 2 of them. Together they'll cancel kilograms squared, and you're left only with meters squared as a unit, and then you're going to root that. So in the end you get meters. So remember to square root this answer. 6.67 to the exponent negative 11. There's a lot to punch in here, so I'm going to make sure to do it carefully in the background here and not hurry through it. And again, I encourage you to try this calculation out to make sure that you can get this on a calculator. The final answer in the end comes out to a fairly known value, 3.8 times 10 to the power of 8 meters as a final answer. Your calculator might actually display it in very long, unscientific format, depending on what type of calculator you have. But that's the final answer, and I'm not even going to check it because that answer shows up quite a bit actually in astrophysics when you get to grade 12. So the practice questions today, there are a couple of them. They're just going to get you to actually repeat these calculations, watch your units, make sure that you convert units to standard metric all the time. And there's a question that rearranges the formula for a different variable. It'll be just like this, but the question in the homework is going to rearrange for one of the masses instead. And then the final question is very much like this example. It rearranges and you solve for distance, and then you have to modify it in the end. So there's only 4 questions. Take your time. You have until Monday, and we'll reconvene on Monday taking up these questions, and then we'll start looking into quiz number 2.